Hi, my name is Michael Chun, and I'll be going over a Python tutorial for machine learning with Google Colab. Credits. This tutorial was originally written by Justin and later adapted by Volodymyr and Isaac and Kevin, and yet again by me. The machine learning course on Coursera taught by Andrew Ng is amazing, but is difficult to do the coding assignments in Python, Numpy, Matplotlib, etc. because he only teaches theory, and I hope that this tutorial and my lecture will help solve this problem. Introduction. Python is a great general-purpose programming language on its own, but with the help of a few popular libraries, Numpy, Skippy, Matplotlib, it becomes a powerful environment for scientific computing. And this is a quick crash course. I hope that you enjoy. In this tutorial, we'll cover basic Python, Numpy, and Matplotlib. A brief note on Python versions. We are currently using version 3.10.12. Basics of Python. Python is a high-level, dynamically typed, multi-paradigm programming language. It's said to be almost like pseudocode, since it allows you to express very powerful ideas in very few lines of code while being very readable. And this is an example using the classic quicksort algorithm. We note that it sorts this array really quickly using quicksort. Basic data types. Numbers. Integers and floats work as you would expect from other languages. So x is equal to 3 and its type is an int or integer. In addition, we can add, subtract, multiply, and exponentiate. We can also add 1 to it, print it out, multiply it by 2, and print it out again. And this is another example using y, which is a float type. We can print it out, multiply it by 2, and exponentiate by 2. Note that unlike many languages, Python does not have a unary increment or decrement operator, and it also has built-in types for long integers and complex numbers, and you can find them in the documentation. Booleans. Python implements all the usual operators for Boolean logic, but uses English words rather than symbols. So we have t is equal to true and f is equal to false, and the type is bool or boolean. Now let's look at the operations. If we print t and f, that is the logical and t or f, that is the logical or, not t is logical not. T is not equal to f is the logical XOR. And indeed these make sense because true and false is false, true or false is true, not true is false, true is not equal to false, and that's true. Strings. We have hello is equal to hello, world is equal to world, and single or double quotes, it does not matter. We can print hello and the length of hello, which is 5. We can add hello to world to make hello world. We can even format it using .format. And there are a lot of other useful methods. So for example, we can capitalize hello to make it start with a capitalized letter, or make them all uppercased, or right justify the string, or center it, or replace a substring within it, or strip out white space. And you can find more in the documentation. Containers. Python includes several built-in container types: lists, dictionaries, sets, and tuples. A list is the Python equivalent of an array, but is resizable and can contain elements of different types. So here we have an array with elements 3, 1, and 2. We can print it out and access the third element because they are indexed from 0. So 0th element is 3, the first element is 1, and the second index is 2. We can even print out from the end. So -1 is the first element from the end of xs, which is 2. We can access the third one and change it to a string called foo and print it out. And note that we can contain elements of different types, so we're not strictly bound like Java. xs.append bar, we can append a bar to the end and print it out. So now we have 3, 1, foo, and bar. We can even pop out, which means remove and return the last element of the list. So we return that element into x and print out x and s and xs. Now we have bar here. Slicing. In addition to accessing list elements one at a time, we can use concise syntax to access sublists. This is known as slicing. So nums is a list from 0 to, and it stops at 5, so 0, 1, 2, 3, 4. We can print out nums and print out 2 to 4. Now note that 2 to 4, we start at 2, at index 2, which is 0, 1, 2, and we stop at 4. So we only got 3, so 2 and 3. We can even slice from the second index all the way to the end to get 2, 3, 4, or get a slice from the start to index 2, so 0 and 1. And we can get a slice of the whole list, so we're just returning the whole thing again to get 0, 1, 2, 3, 4. And we can even print out slice indices can even be negative. And so it would stop at the last element. So we would get rid of that 4. We can assign a new sublist to a slice. So nums 2 to 4 would be equal to 8 and 9. So it would change it. So now we would print out 0, 1, 8, 9, and 4. Loops. We can loop over the elements of a list like this. Animals is equal to cat, dog, and monkey. And for each animal in animals, we're going to print out the animals. So cat, dog, and monkey. If we want to access the index of each element within the body of a loop, we use the built-in enumerate function. So this lets us see the index of the animal. And we add 1 because the IDX starts from 0. And we wanted a number 1 over here. List comprehensions. When programming, frequently we want to transform one type of data into another. As a simple example, consider the following code that computes square numbers. Okay, so square is a blank array, and for each element in nums, we square it. So 0 squared is 0, 1 squared is 1, 2 squared is 4. You get the idea, and we print it out. We can make the code simpler using list comprehension. So list comprehension makes our code shorter. And we can also contain conditions. So mod 2, if x mod 2 is 0, then we would print it out. So mod 2 just means even numbers. So we want to only print out the even squares. Dictionaries. A dictionary stores key value pairs similar to a map in Java or an object in JavaScript. So we would say that a cat is cute and a dog is furry. And we can print out d bracket cat to get cute. And we can even see if cat is in d, and that would be true. And we can even create more elements. We can say that a zebra is funny. And when we print out zebra, we should get funny. And we can set an entry in a dictionary. So we can say d bracket fish is wet, and print out d bracket fish, which is wet. Now how about d bracket monkey? So we got an error because monkey was not a key inside of our dictionary. And indeed the error over here says that's a key error. Monkey not a key of D. Now we can print an element Let's try to get monkey and fish. And we see that we got n/a for, which is the default because monkey was not inside of our dictionary, and what was accessed by fish. We can delete fish and see that it's not there anymore. It's easy to iterate over the keys in a dictionary. So for animal legs inside of d.items, so that's the whole dictionary, we can see the number of legs each animal has. A person has 2 legs, a cat has 4 legs, a spider has 8 legs. Dictionary comprehensions. They are similar to list comprehensions, but they are for dictionaries. So we are squaring numbers again. If x mod 2 is equal to 0, so if x is an even number. Set. It is an unordered collection of distinct elements. Here's an example. We have animals is equal to cat, dog, and we can print if cat is in animals, which is true. And how about is if fish in animals? It's not, so we print out false. We can keep adding stuff to it. So we add in fish, and now we ask the question, is fish in animals? And it's not, so it is, sorry. And so we would return true. Print out the length of animals, which is 3. We can add cat to it, and now the length of animals is 1 longer because there's 1 more element. So 2 plus 1 is now 3. And if we remove cat, then it becomes 2 again. Loops. Iterating over a set has the same syntax as iterating over a list. However, since sets are unordered, you cannot make assumptions about the order in which you visit the elements of the set. So when we print this out, it's not necessarily in the order of cat, dog, then fish, but rather is unordered, meaning that dog came first, then cat, and then fish. Set comprehensions. Like lists and dictionary, we can easily construct sets using set comprehensions. So we are squaring the x's in this one. We're square rooting the x's within the range of 30. Tuples. A tuple is an immutable ordered list of values. A tuple is in many ways similar to a list, but the difference is that tuples can be used as keys in dictionaries and as elements of sets, while lists cannot. Here's an example. So the type of T is a tuple, but notice the syntax is slightly different with the parentheses. And we can print out d bracket T, which is 5, and then print out d bracket 1, 2, which is 1. Now notice that t bracket 0 is equal to 1. It doesn't work because we can't modify the tuple. Functions. Python functions are defined using the def keyword. Here's an example. So this function is called sign, and it takes in a parameter x, which is an int. If x is greater than 0, return positive. Else if x is less than 0, return negative. Else we return 0. So for x inside of this list, -1, 0, and 1, we print out the sign of x. And the sign of x would be first negative, then 0, then positive. We will often define functions to take optional keyword arguments like this. So this example, we have another function called hello and name, and we already set loud to false. So if loud, so loud is false, so it jump to the else, and it would print out hello, but it would format it to have an exclamation mark after the name. So hello Bob. And these are two examples which call the function hello. And this one would be loud is true. So if loud is true, then it would print out hello Fred, but without the exclamation mark. And it would also uppercase all the elements in the name. So notice that Fred is now all capitalized. Classes. The syntax for defining classes in Python is straightforward. Constructor looks like this. The instant method greet looks like that. And it calls the methods like this. And g equals greater Fred creates an instance of the greeter class. And we can call its method g.greet, and we can call another method of g.greet. Now we're going to go over some libraries for machine learning. Numpy. Numpy is the core library for scientific computing in Python. It provides a high-performance multi-dimensional array object and tools for working with these arrays. To use NumPy, we first import the Numpy package. Notice we name it as np. Arrays. A NumPy array is a grid of values, all the same type, and is indexed by a tuple of non-negative integers. The number of dimensions is the rank of the array, and the shape of an array is a tuple of integers, giving the size of the array along each dimension. Okay, we can initialize NumPy arrays from nested Python lists and access elements using square brackets. So this is a rank 1 array, 1, 2, 3. Rank 1 means dimension 1, and the type of A is numpy.nd array. The shape of A is 3, so there are 3 elements inside of it. A bracket 0 is 1, then 2, and 3. Pretty similar to the list from above. A bracket 0 is 5, so we're changing an element of the array to be 5 and printing out A. So now there is a 5, 2, and 3. This is a rank 2 array, so it is a 2-dimensional array, and we're printing it out. The shape of B is 2, 3, meaning so it's in row column format, so there are 2 rows and 3 columns. We're printing out some elements, so 0, 0 would be this 1, 0, 1 would be 2, 1, 0 would be 4. Numpy also provides many functions to create arrays. A equal to np.zeros 2, 2, so we have 2 rows, 2 columns, and is an array of all zeros. We can also create an array of all ones and create a constant array with a value that we set by ourselves. So in this example, it's a 7. It could also be a 9. And we could even change these row column variables. So now I want 3 rows, 5 columns. And indeed, 3 rows, 5 columns. D is equal to np.I2. So I stands for identity matrix. And we have 2 rows, 2 columns. And notice how the row and column is the same. And that the diagonal is all ones, which is the identity matrix. Now equal random 2, 2 is an array with random values. And notice how when I run it again, I get different values because they are random. Array indexing. Numpy offers several ways to index into arrays, such as slicing. Similar to Python lists, NumPy arrays can be sliced, and they may be multi-dimensional, so you must specify a slice for each dimension of the array. So we have an array that looks like this now, 1, 2, 3, 4, and so on, and we can slice it. So A bracket 2 slices the first 2 rows out, so it would be this this part of the matrix or array, and we want to pull out the columns 1 and 2 next, so that would be this part of the matrix, 2, 3, 6, 7. A slice of an array is a view into the same data. So modifying it will modify the original array. So we have to be very careful. So A bracket 0, 1 is row 0, column 1 is 2. And when we modified B bracket 0, 0, that's this 1 over here, to be 77 and print it out again, notice that it now becomes a 77. You can also mix integer array indexing slicing with slice indexing. However, doing so will yield an array of lower rank than the original array. And this is quite different from the way that MATLAB handles array slicing. But MATLAB is from 1,000 years ago or something, so we don't need to worry about that. Create the following rank 2 array with shape 3, 4. So 3 rows, 4 columns, and it looks like this. Now we're gonna access data, but in different ways. So we are accessing the second row of A with different ranks. So these two have a rank 2 view, and this one, or I should highlight this one, these two have the rank 2 view, and this has the rank 1 view. So the rank 2 view has this additional brackets surrounding 5, 6, 7, 8. And we can make the same distinction when accessing columns. Integer array indexing. Integer array indexing allows us to construct arbitrary arrays using data from another array. Here's an example. So we have A, which is a Numpy array over here, and we want to slice it using another array. So in this example, 0, 0 is 1, 1, 1, so these are rows and columns, 1, 1 is 4, and 2, 0 is 5. And this does the same thing, but I think in a more readable way. 0, 0 is 1, 1, 1 is 4, 2, 0 is 5, and we're printing it out. When we use integer array indexing, we can reuse the same element from the source array. So this is 0, 1, so 0, 1, but print it out another time. So one useful trick with integer array indexing is selecting or mutating one element from each row of a matrix. So we're creating a new array from which we'll select elements, and here are indices that we want to select. Now in this example, mp.arrange4 is allowing us to do like a 4ion range of 4. So we're going from the top array to the bottom of the array. So first array, we are gonna go for the 0th column, so that's the 1. Then the second column, second index will be 6, 0th will be 7, 1 will be 11. And we can mutate these specific elements. So notice how all the elements 1, 6, 7, and 11 now have 10 added to them. Boolean array indexing. So I'm not going to go over in detail, but you can. So these are selecting elements that are greater than 2 and printing them out if it is greater than 2. And this one is doing the same thing. Data types. Every Numpy array is a grid of elements of the same type. Numpy provides a large set of numeric data types that we can use to construct arrays. And so here's an example. If we let NumPy choose the data type, then it's going to automatically choose int64 for us. 64 meaning the number of bits. Y is, so we're letting it choose again, but it's now saying that's a float 64 because we have floats inside of it. And if we can even force a particular data type onto it, so we're saying d type or data type is equal to np.int64, and we're printing out the types over here. Array math. Basic mathematical functions operate element-wise, so that word is important. It means for each element on arrays, and are available both as operator, no operator. So operator is like a plus or a minus or a times or a divide, etc. And as functions in the NumPy module. So functions like dot array or dot add or dot subtract or dot multiply or dot divide, dot, you get the idea. So now we're doing an element-wise sum, which will produce a new array. So we're adding all the elements of the array from x to y and getting this new array. And we're also using in a different way, which is dot add. We can subtract, we can multiply, we can divide, we can square root. And notice that unlike Matlab, times is an element-wise multiplication, not matrix multiplication. For matrix multiplication, we use a different function called the dot function, and we'll go over that. So x and y are these NumPy arrays, and we can take the inner product of vectors v and w together, which will produce 219. We can use the at operator, which is equivalent to the dot operator. So these are matrix vector products, and will produce an array, a rank 1 array 2967. We can do matrix product, which will be this rank 2 array, but in different ways. So note that we're doing x.y and then np.xy, and we're using this at symbol. And they're all producing the same result. So NumPy provides many useful functions for performing computations on arrays. And one of the most useful is sum. So we want to sum all the elements of this array together, which is 10. And we can sum each column, and we can sum each row. So for example, 1 plus 3 is 4, 2 plus 4 is 6. And if we want to just get the columns or the rows together, then 1 plus 2 is 3, then 3 plus 4 is 7. And we can even manipulate the data. So for example, we are transposing x. So transposing, we are flipping the rows and columns together by using .t. Broadcasting. Broadcasting is a powerful mechanism that allows NumPy to work with arrays of different shapes when performing arithmetic operations. Now, for example, we want to add a constant vector to each row of a matrix. We can do it like this. So we have this vector v over here, 101, and this matrix x over here, and we want to add 101 in this order. So 1 plus to every single row. So this row will have 1 plus 1 on it, 2 plus 0, 3 plus 1, and the same is applied to this row and this row and this row and this row. And we're just setting it an empty matrix over here and adding it with this loop. Now this works, but when matrix X is very large, it could be very slow in Python. So we could do it a faster way with numpy.tile. and we could use the plus operator to do the same thing. Numpy broadcasting allows us to perform this computation without actually creating multiple copies of V. Now this is doing more broadcasting, and you can pause and read all of the rules if you want to. And there are even more explanations from the documentation. Here's some applications of broadcasting. So we could do an outer product of vectors, add a vector to each row of a matrix, add a vector to each column of a matrix, reshape it, multiply it by a constant. And so broadcasting makes our code more concise and faster, so we should use it whenever possible. And there are more rules in the Numpy reference. Matplotlib is a plotting library. We give a brief introduction to the matplotlib.pyplot module, which provides a plotting system similar to that of MATLAB. So we import it as PLT. This special IPython command displays the plots in line. Plotting. The most important function in Matplotlib is plot, which allows us to plot 2D data. Here's an example. So this plots out the sine function. With a little bit of extra work, we can easily plot multiple lines at once and add a title, legend, and axis labels. So now we have the cosine function as well, and we're plotting them. Notice how the x label is set to be x-axis label, y label is y-axis label, the title is sine and cosine, and the legend is sine, cosine. Subplots. We can plot different things in the same figure using the subplot function. So now we have two separate plots, sine and cosine. You can read more in the documentation. Thanks for watching.